Hello and welcome back. Before we continue on with our notes, I do want to talk about the difference between what a vector field is and a slope field is. Back in Calculus 1, single variable calculus, we learned about slope field. There's this amazing video on YouTube. I can tell you all about it. And a slope field, what we talked about last year, is it will give us the shape of a function. And I kind of do like a little cheap little slope field down over here for us. If I were to land on any graph, any point on here, the slope field gives us the path we're going to take on that function. In other words, it'll give us the shape. Remember, there are infinitely many of these little paths, but only one would have at a specific point. And a vector field is very similar to a slope field, but it doesn't give us the shape of the function. What it's going to do is like a vector. It just gives us the direction. You might remember earlier this year, we compared the difference between the function and a vector, where a function could be a road. It's like a road, where a vector, it's the path. So where a function is a road itself, like if you look outside your house right now, you'll see a road. The road goes in any direction. When you get in your car and you drive, you're going to drive along a path. Now, ideally, your path will be on the road. If not, you're going to have to deal with your insurance company with that one. That is beyond our class at this point. So, ideally, we want that path to be the road. But it doesn't always have to be. We'll talk about that in just a few moments. So what we're going to say is here, so if I'm given a vector field, if I'm given a point on that vector field, what the difference is a vector says I'm specifically only going in a direction. Now again, ideally, the direction should follow the path. Direction follows the path. That's the ideal. In other words, we would say our slope field, which we can say is our derivative, will equal our vector field. So we would say that the slope field has to equal our vector field. That's the ideal that we want. We want our direction to follow the path. And if this happens, as a result, we can actually solve for the original function. We can solve for the function itself. Now, the original function. Now, why do I say the original function? Because remember, both the slope field and vector field involve derivatives. Like our vector field is our partial derivative, the derivative with respect to x, the derivative with respect to y. Our slope field is, of course, the original derivative, dy dx. So if they're the same, we can solve for our original function, and we did this last year using differential equations. We solved differential equations. And we're going to do this in another lesson. Now, the next question is, well, what if they're not the same? Well, if they're not the same, in other words, let's say we veer off the road. Let's say my direction goes off the road. Well, that's a big no-no for us. In that case, because the vector field and the function and the slope field are not the same, we won't be able to solve for a potential function, what we call a potential function, or the original function. And that's another issue for a later time. So we want them to be the same. And there is a way we can tell that they're the same, but again, that's going to be in another video. We're not quite old enough for that yet. Now, we do have a special name that if the slope field and the vector field are the same. We call this conservative. Okay, and so let's now talk about that. Okay, so if the vector field is also the gradient, remember, so if my vector field is also my gradient, then we say this is conservative. So what we're saying here is that the vector field and the slope field are going to be the same. If we think of the gradient as giving us the slope or the direction, then our vector field and the gradient are the same. So we're heading in the same direction. We are going to say that this is called conservative. So in other words, we're going to say that the vector field is the same as our gradient. I kind of switched those around. So in other words, our path is on the road. So these are in the same direction. If they're in the same direction, we say that this is conservative. So what we're asked to do is find the conservative vector field for the following. Well, if we already know it's conservative, we already know, because they're telling me it's conservative, we already know that if I want to find my vector field, it's the same as my gradient. So I'm just going to go and find my gradient. So my gradient, which is the same as my vector field, will be, what's that? 2, 1. And there's my answer. That's it. I already know it's conservative. Now later on we're going to tell how can we tell if they're conservative or not. We'll see that. Now, if we want to see if a function is conservative, we can use the following test. And this is a test for conservatives. Okay? If you can't pass this test, I guess you would just be considered a rhino. So we want to test if this is conservative. So given the vector field, so the vector field fxy is equal to minj. Remember, this is talking about the slopes right here. So we're going to use the slopes, our gradient. Whoops, excuse me, let me erase this. We are going to assume the gradient, so this is going to be our slopes right there. If the vector field is conservative if the partial of n with respect to x is equal to the partial of m with respect to y. This is our test. Now, this comes from the vector field. Or the derivatives. We're looking at the derivatives of our vector field right now. So if I look up here, I know that my vector field can be written as, well, this is going to be m, and this is going to be n. So this is going to become 2i plus 1j. So there's my vector field. So for my test, I would take the partial of m with respect to x, see if that's equal to the partial of m with respect to y. Well, what's the partial of n with respect to x equal to? Well, there is no x here, so it's just 0. The partial of m with respect to y, here's m, there's no y here, it's also going to be 0, so this checks out. So they're the same, so therefore our vector field is conservative. In other words, what is that telling me? This is telling me that the path we are on, or let me rephrase that, this is telling us that the direction we are going is on the path of the function, is on the path. That's what that tells us. So if we go back down here, and that tells us that if this is my slope field, we're heading in the direction along that slope field right there. And we're going to spend a little bit more time in this in the next couple of days. So since the vector field is a slope, we can use conservative vector fields to find a potential function. Of course, this is going to involve integrals. Like I said, this is our differentials from last year. But we'll talk about that later. All right, so I hope you enjoy these videos. I will see you all later. Bye-bye.